Yes, so if we think of the nodes of the graph, there's no natural order relationship on the nodes of the graph typically, right? So any kind of function that we learn across structured data should be invariant under permutation of the nodes. So that should capture a permutation invariance. And we can play this game much more general. We can think of all sorts of symmetries that might arise in data, that might arise in various domains where our data is coming from. And then this can be used for structure that we can encode in our model geometry. So this will be one setting that we consider in this talk. And, yeah.
Okay, it was muted. I think we're okay now.
Yes. So learning out of symmetries is our first setting. And then we also want to consider a second setting, namely where we have low dimensional structure in our data. Right. So you probably heard of this term, the manifold hypothesis. So very often when we work with high dimensional data, we make that implicit assumption that the data actually lies on or near some low dimensional manifold, and that structure in our data set, in our domain, that could also be something that might influence the learning complexity of our problem, for instance, like learning neural networks. So that's a second geometric setting that we want to consider in this talk. Okay, but let's start with learning under symmetry. So many in the audience probably sort of know what supervised learning is, but just so that we're all on the same page, let me briefly sort of introduce the setting that we're considering here. So we will only look at supervised learning tasks. So in supervised learning, we have some labeled data set that we can use to train our model. So our data set consists of some pairs of data points and labels, xi and yi, that are drawn from some distribution over the data and label space. Typically, we assume that the data space here is some high dimensional Euclidean space, which again might have some additional structure. And then we assume that there's some functional relationship between the data points and the labels, right? There's some function f that's typically unknown to us. And all we know about this function f is the functional relationship that we can get from our data. So we assume that those labels yi is exactly the output of that function if we input the data point xi. And then our learning problem is to find a function f tilde that approximates this function, right? So if we put one of our data points xi into f tilde, then we should get yi or something very close to yi. And then the model architecture, say in our case, the architecture of our neural network, that will determine how exactly that function class f looks like. Right, and many architectures or methods that we might consider in machine learning can be phrased in this setting. Here we're mostly interested with neural networks, right? So neural networks represent trainable functions. Here the parameters are the weights of the network. So that could be one function class f. But also more generally, if we think of problems like fitting polynomials up to degree k, for instance, that can also be seen as an instance of this problem. Okay, so the first and the sort of classical setting that one usually considers is sort of a geometry agnostic setting, right? So this would be, for instance, if we have a feed-forward neural network, we might put some assumptions on how specifically that architecture looks like, but for the purposes of this talk, you can just think of a simple feed-forward neural network. And that is, at least in the first part of the talk, contrasted with a learning setting where we have symmetries, where we have geometric structure. So here we consider a restriction of the function class f to f sub g, and that contains the subset of all functions that are invariant under elements of the group G. So the group G here characterizes the symmetries in our data, and then invariant here, of course, means that if one of the group elements acts on a data point, then that shouldn't change the output. Right, that was like we had earlier an example with the image classification. If we translate the object with the image, then the label dog should not change. Okay, so what types of model architecture could allow us to learn such a symmetric function class? Typically what we use in geometric machine learning, you might have heard the term geometric deep learning, and we typically use equivariant neural networks. And equivariant neural networks look sort of structurally, in terms of the building blocks, quite similar to standard deep learning architectures. The key difference here is that we're replacing the linear layer that we have, for instance, in a standard feed-forward network with an equivariant layer. And then the other building blocks that we might have, such as activation functions, pooling operators, we then also have to adjust in a way that the geometric structure that's encoded in the base layer is preserved throughout. So very generally, sort of without going into specific details of specific proposals for how to construct such equivariant neural networks, I should say there are many different proposals for how to build such equivariant layers. So how to adjust this base layer to be equivariant, to respect the geometry of the data. But all of them have in common that it looks something like this, right? So in order to achieve equivariance, we require that if an element of the group acts on the input, then that should affect the output of the layer in the same way, right? So that's this condition. Okay. So for the purposes of this talk, we sort of have to just have in mind generally what kind of how such an architecture should look like. And we will see one specific example later on in the talk, but all of the architectures you can think of as being of this form, and then the specific structure of the layer is of course determined by what group, what symmetry we are encoding. And this idea has been really, at least empirically, very successfully applied across domains. We already talked about images and convolutional neural networks. We also mentioned graph neural networks. And so deep sets is very similar to graph neural networks. That's an equivariant architecture for set structured data. But you could consider all kinds of other domains, such as point clouds, for instance, where you want to preserve Euclidean symmetries, so translation, rotation, and reflection. Maybe your data lies on a sphere, so that's a parameterization that recently has gotten a lot of interest in climate modeling. And there you want to preserve rotation invariances. So the group that you would be encoding is the SO3. So for many different geometric settings like this, architectures have been proposed, and at least empirically, it does work well. And it also, at least empirically, helps with achieving the goals of mitigating these like high resource requirements. So very often in this geometric setting, we do find that we can get away with smaller models that can be trained with fewer resources, and that also typically for in a data scarce setting, these geometric architectures can work. Okay, so this is sort of just to so that we have in mind how these architectures could look like. And now let's actually think about how we could analyze the complexity of those architectures and really where the geometry comes in. So one tool that we might want to use to study the complexity of a learning problem is sample complexity, right? So if we have a given function class, so this could be a class of functions that the neural network can represent, the unknown functional relationship that we want to recover is f star. And then we could ask how many data points do we need to find a function g that is an epsilon approximation of f star in some metric on the function class. Right. So essentially what we want to get with this is an upper bound on the number of data points that we would need to learn a good approximation to the underlying functional relationship. And for standard feed-forward neural networks, so geometry agnostic architectures, that's been analyzed. And what we typically find is that the sample complexity here scales polynomially in the number of parameters, right? So this is one example from a paper that's like about two years old that analyzes the class of functions that can be represented by a one hidden layer feed-forward neural network. And then you see here with the parameter budget W, so you see here the polynomial dependency. So that's good, right? Generally, polynomial time means we can, at least from the perspective of sample complexity, it's efficient. So that's good news. Now we can ask, what about symmetries? So if we now encode symmetries as inductive biases, so we use equivariant neural networks, we restrict our attention only to the symmetric functions. What kind of impact does that have on the sample complexity? And what we see sort of broadly, the trend that we're observing, this has mostly been analyzed for special instances of equivariant neural networks or for special geometric setting. But the sort of general trend that we see is that geometric inductive bias reduces the sample complexity by a factor that is proportional to the size of the group. Right? So that's been analyzed in a variety of different settings. So the first one here, for instance, group convolutional neural networks. That's one like very widely used instance of the equivariant neural network that we saw earlier. Then from my group with collaborators at Google, we looked at classification problems in hyperbolic space that would also fit into this setting. Right? Hyperbolic space here, the symmetries are the Lorentz group. And then also other machine learning settings such as kernel regression under symmetry, for instance, has been analyzed. And in all of those settings, we see those kind of patterns emerge. However, I should say here sort of from a complexity theory perspective, even without encoding this geometric structure, we're already in an efficient setting where we already have polynomial complexity. It's of course great to get a reduction in a factor that's proportional to the size of the group. So geometry certainly helps, and it helps in a way that we can measure. But even before that, even in the geometry agnostic setting, we already, from the perspective of sample complexity, are in an efficient setting. So now we could also look at a different measure of complexity, namely runtime complexity. So here we're not looking at sort of the budget in terms of data, but something closer to the budget in terms of compute that we would need. Right. So again, we look at some function class that we can represent with a given model architecture. We want to learn f star in the sense that we want to find a function g in our function class that's an absolute approximation of f star. But now we are asking what's the computational runtime that is needed to perform to find g, to find a solution. And here, so what do we mean by runtime? So runtime is essentially, you can think of that as a step of your learning algorithm, right? So typically neural networks are trained with gradient descent or with a variant of gradient descent. And if we think about performing one step of gradient descent, the sort of main work that needs to be done, or what we need to measure in a sense, is the gradient or a gradient estimator, right? So such a step we typically call in this setting the number of queries. So roughly speaking, we are interested in evaluating how many calls to the gradient oracle or to the gradient estimator we need to find a sufficiently good solution to our learning problem. Now, this perspective on complexity, that is the so-called statistical query model, which was introduced by Michael Kearns. I put here the technical definition, but I think it's best illustrated on the stochastic gradient descent, which is really the main learning algorithm that we care about in this setting, again, because that's what we usually use to train neural networks. So in the statistical query model, the idea here really is to abstract away a lot of the sort of details of the optimization approach and to break it down to this number of queries, this number of steps that we need to perform in the learning algorithm. So we define a query function that sort of encodes what has to be measured. So in our case, that's roughly speaking a call to the gradient oracle. And then we have some tolerance parameter that sort of controls the accuracy of what we get from the oracle call. So if we look at what this means on the example of stochastic gradient descent, right? So here the query function would return the gradient of the mean squared error. or like an estimate of it in the, like a gradient estimate in the stochastic setting, and then up to some error. And in the stochastic gradient setting, that error that is typically controlled by hyperparameters, in particular the batch size. Right? If we have a large batch size, that means we get typically a more accurate estimator. So that the tolerance parameter that we would be defining here in this setting, if we analyze stochastic gradient descent as an instance of this setting, then our tolerance here would be guided by the batch size. So let's again look first at what happens in the geometry agnostic setting, right? If we just look at feed-forward neural networks. And that's been analyzed in the SQ setting. So here in the theorem statement, this is a result by Diaco-Nicolas et al. And here you see the term correlational SQ algorithm. So SQ algorithm is any algorithm that can be phrased as in the statistical query model. And then correlational here, that's a special case or a restriction of that, which for the in the interest of time, I'm not gonna introduce, but stochastic gradient descent is an instance of that particular subset of the SQ model. And then Diaco-Nicolas et al. Showed that from this perspective of runtime complexity, we can actually not efficiently train neural networks, right? So what they showed here is that the query complexity is exponential in the size of the input. So this is a worst case analysis. It doesn't mean that we can't train any neural networks, right? But there exist certain functions, certain function classes that we cannot, that can be represented with a shallow neural network, but we can't efficiently train that neural network, even with a simple data distribution such as IID Gaussian data. Okay, so unlike with the sample complexity, if we take that perspective of runtime complexity, we are not in an efficient setting. This is like an exponential, we have an exponential time algorithm in this setting. So now bringing in this geometric perspective, a natural question that we can ask is, what about those invariances? If we bring in those invariances, if we look at an equivariant architecture, we restrict our function class to the symmetric functions corresponding to the respective symmetry. Does that help us at all with this impossibility result, with this exponential dependency? Unfortunately, here the answer is no. So geometry, or at least this type of geometry, cannot circumvent this fundamental hardness of learning neural networks. We do get, as we would expect, a similar reduction to what we see in the sample complexity setting. So again, we get some factor that is proportional to the size of the group that gives us a reduction in the complexity, but that is not enough to go from exponential time to polynomial time. Yeah.
Are these lower bounds you're speaking of basically information theoretic? Is it that there's they're doubly exponential number of functions, so we'll take exponential and then queries? Is that
So I'm gonna, no, not quite. I think, but I'm gonna give an example in one of the next slides on how we get to that, and maybe if it doesn't answer your question, we can go back. But I think so. I should preface this with, so the statistical query model is one of many complexity models, right? You might be familiar with pack learning, for instance, right? There are other models of analyzing learning complexity. We are particularly using the statistical query model because gradient descent is like a very simple instance of that. And that's sort of the learning framework that we care about. I think what you're describing is probably a different learning setting. Yeah. Okay, so just to, let me just finish this slide to your question. Yeah, so the two key findings here that we get this reduction in the complexity by a factor that's proportional to the size of the group, but we can't, but just by encoding symmetries as an inductive bias, we can't overcome this fundamental hardness. So we're still in a setting where we have an exponential time dependency on sensitivity. And sort of the conclusion from that, and we will revisit that in the second part of the talk, is that we need some additional structure. So just merely encoding symmetries is not going to be enough. We have to think about what other structure we might have and how that could help us make more progress here and maybe reduce the complexity further.
What happens if G is an infinite group? What's the
But this is for
minimum?
finite group.
You only consider finite.
Yes, I only consider finite groups in this setting. Things are much more complicated if you're in this setting.
So when you speak of translational symmetry, are you looking for us for that definitions?
With the images,
Well, you said finite group, and I think translations in the group, so.
oh, we were on a grid, like in the image setting, it's like a pixel space.
Yes.
Yes. And then, yeah, you have periodic.
Periodic.
Yes, periodic boundary conditions, and you're on a grid. Yes, so you can phrase that as a problem. Yeah. Yeah, if you go beyond finite, anything, I might not have mentioned that explicitly earlier. I hope it was on the slide, but yes, everything we're saying here, this is for finite groups. Once you're in beyond that setting, a lot of these tools or things that I was saying here do not apply anymore. So that's very, very important, finite groups. Yes, so just to, this was sort of the general findings. Let me zoom in a little bit on what we can say about specific geometric architectures. So explicitly worked out, we have 3 settings in the paper. The first one is sort of more of technical or theoretical interest, namely that looks at invariant Boolean functions. That's not typical, something that we encounter very often in the geometric machine learning literature. But sort of from a historic perspective, a lot of the early work on the statistical query model has been considering Boolean functions. So looking at sort of the symmetrized version of that, learning invariant Boolean functions is a sort of simple entry point to trying to understand how some of these classical tools from complexity theory could apply in the geometric setting. But then more interesting, of course, is to study actual geometric architectures, or architectures that are representative of what people actually use in practice. And then here a prime example, of course, are graph neural networks, right? That have been or is by now the most popular architecture used for graph structured data. And many of those graph neural networks that you see in practice are based on message passing. So they're also transformer style architectures, but a lot of the graph neural networks that are used in practice are based on message passing. So for that setting, we have performed a detailed analysis. And in the graph structured setting, there are sort of 2 parameters in our data that sort of characterize the size of our data, if you like, in a graph. So that's one, the number of nodes, and then it's also the feature dimension. So in many applications where we use graph neural networks, our input are attributed graphs. So we not only have the adjacency of the graph, but also a feature vector associated with each graph. And then we have hardness both in the number of nodes, so in the size of the graph, and then also in the feature dimension. And then a third setting that we are analyzing would be the sort of most commonly used instance of that setting would be convolutional neural networks. But we write this in the more general setting of symmetrized or frame averaged neural networks. So that is a setting that encompasses a lot of those equivariant or a lot of the equivariant neural networks that are used in practice could be written as an instance of this frame averaged or symmetrized neural network framework. And that one, I want to give some more intuition or sort of illustrate the intuition of these results on. I'm not going to give too much details on the graph neural networks setting, because there the construction is sort of a bit more technical and probably beyond what we could even give intuition on in a talk like this. Yes, so symmetrized neural networks. A lot of the geometric deep learning architectures, including some that we mentioned earlier, like convolutional neural networks or deep sets. So that was the permutation-invariant architecture for set structured data. A lot of those architectures can be essentially understood as symmetrizing more general function class. And symmetrizing in the sense that we apply a group average, like what is written here, to restrict our function class. So we take a geometry agnostic function class, if you like, and then we apply the symmetrization, and that gives us the symmetric function class. And in this kind of setting, we again here you can sort of probably imagine how one can derive that you get this vector reduction. That's like quite easy to see with this perspective of symmetrization. And then that it doesn't overcome hardness. here, like one example to look at, so the convolutional neural networks that we've discussed a couple of times now, and those can be written as symmetrizations of classical feed-forward networks, right? And we know from Diakonikolas et al. And related work in that direction that those feed-forward networks themselves are hard to learn. So there we have an exponential dependency. And now, we get this factor, but of course that doesn't get us from exponential to polynomial. Right, and then this is sort of writing it very hand wavy, but if we put that all together, we get a precise guarantee and we get an exponential lower bound on the runtime complexity for this class of symmetrized networks.
Quick question to try to understand correctly. If you're taking that average, it means that you're finding the value of the function more times, like with the same cardinality as g, right? Does that mean you have to make way more calls to the SG to get the gradient for all of them, all of those nodes, or you get one single?
But so this is just a construction of how we get those function classes. This is not sort of what happens under the hood necessarily in an equivariant neural network. Just a function class that those networks can represent can be connected to a geometry agnostic function class, or function classes that can be represented by geometry agnostic architectures such as feed-forward networks. We can make this connection. So it's more like a theoretical tool, but it's not necessarily what we do in practice for efficiency reasons. Yeah, but it's a good question. I also want to show you some experimental results. So again, this runtime complexity analysis is sort of a worst case analysis, right? We want to construct a class of functions that attains some lower bound that's exponential. That's how we show hardness. So this is by no means something that always happens in practice. And we know that both feed-forward neural networks and geometric architectures can in many settings be trained effectively, right? That's, of course, it is that way. Otherwise, we wouldn't be able to use those methods in practice. But for those instances that we construct, we do also see experimentally that, like, in fact, they can't be trained effectively. So what you see here on the slide, this is we didn't go over this, but so we constructed one sort of pathological example of a function class that can be represented by a shallow graph neural network, but cannot be efficiently trained. And then we also constructed, this is for the CNN case, so a class of functions that can be represented by the symmetrized frame averaged neural networks, but cannot be efficiently trained. Or that's at least what the theory indicates. And here in practice, you see this as well. So over here, for instance, you see that the network essentially doesn't train at all, right? Training curves are just, they don't move, like no training happens. And then over here, we see that the training happens, like the training loss goes down, but the test loss doesn't move, right? So this just overfits, but it doesn't really meaningfully or give us a good solution, right? So this is, of course, synthetic examples, right? We constructed those classes theoretically, and then we just implemented the corresponding architectures. So those are not representative of something that you would find in practice, but it shows here that the prediction from our theoretical analysis is something that we could also observe in sort of real time if we test this out in a computer. Okay, so how can we interpret those results? So what kind of conclusions can we get from that? So certainly our intuition, I guess, that we would get from this literature on geometry and sample complexity does also extend to runtime complexity, right? We have this reduction of the complexity in a factor that's proportional to the size of the group. But we can't get around this exponential dependency. So there are instances of functions that cannot be efficiently trained with equivariant neural networks. So these fundamental hardness limitations that we have that are established for feed-forward geometry agnostic neural networks, those extend to the symmetric setting. So as we already said earlier, in order to potentially overcome this, we need to go beyond symmetries, right? We need additional assumptions on the architectures, on the model class, or additional assumptions on the data to potentially overcome those results. But symmetries alone will not do the trick. Okay, and then just to note here again, this is of course a worst case analysis, right? We are by no means indicating that, like in practice, those architectures can't be trained in many settings. This really works very well. This is more to understand sort of fundamental properties of these architectures. I think it's like a fundamental problem to understand the learning complexity, and then perhaps from those failure modes that we're identifying with this analysis, we can also perhaps get some guidance on how to maybe improve the architectures that we already have. Okay, that brings us to the second part of the talk.
Question for you. So part one was about functions that are difficult to learn. What should we have in our heads? What's an example of a random function? The function is values that are randomly generated. I just don't have a concrete example.
Yeah, so unfortunately, so those function classes here are not very intuitive. They're really like constructed in a way to make the proof work.
Give us some idea. Sorry.
So in the graph neural network setting here, the class of graphs that we start with are like Erdős-Renyi graphs. And Erdős-Renyi graphs, it's like a random graph. Erdős-Renyi.
Oh, random. Yes. Sorry.
Yes. So it's a graph model, right? That is used like very frequently in graph theory to study the structure of graphs and sort of with different properties. And then we define here kind of like a Boolean function on Erdős-Renyi graph. So this is where the construction goes. But it's not very intuitive. I couldn't tell you an application where you would encounter such a structure. So it's really like a construction. Yeah, I'm not sure if that helps.
Can I actually ask about that too? I was kind of wondering a similar thing. So like, you take one of these functions that's hard to learn for just the unstructured neural network. You just try to map it into like the fundamental domain, like you could just quotient by Euclidean finite group, and just sort of like, take that function and reproduce it there and just extend it symmetrically. Is that like an example of something that's hard to learn?
Yeah, that's sort of with this frame average setting, that's how those were constructed. Right. So in the classical literature, or like this Diakonikolas et al. Paper, for instance, they construct also very abstract function class, like nothing you would encounter in practice, right? And then we are thinking about how to map the sort of similar construction into the geometric setting. So not everything translates one-to-one, but it's certainly a very good guidance to look at those first. Yeah, that's the idea.
I guess you might be, but I was wondering, like, under the manifold hypothesis, is it easier to learn these sorts of functions?
Let me get to it. Okay. Yes. So so we need additional assumptions, right? Either on the network architecture or on the geometry of the data. And in the second part of the talk, we're focusing on the data geometry. So we're moving away from the symmetric setting, and we're going back to the setting where we assume that we previewed earlier, where we assume that our data lies on or near a low-dimensional manifold. So the kind of learning setting that we're considering here is here we're not making any sort of inductive biases on the network. We're sort of using a standard feed-forward neural network, or that's the class of functions that we're considering. But now we are sort of refining the geometric analysis of our data set, of our data manifold. And namely, we're looking at smooth d-dimensional submanifolds in the n-dimensional hypercube. That's mostly like a theoretical a condition and assumption that makes the analysis nicer, but this smooth d-dimensional submanifolds, that's important. So that's the low-dimensional structure that we're considering. And then we also have to, it's important to take the geometry of the data manifold into account. And in particular, to look beyond just the dimension, the intrinsic dimension of the data, but also at the curvature of the manifold. And curvature, so I won't be able in this talk to sort of go deep into differential geometry, but you probably know that there are many ways of measuring curvature in differential geometry. Two such notions are the Ricci and Ricci curvature. Ricci curvature is an intrinsic notion of curvature that would take probably a bit more time to explain, but the Ricci is sort of very intuitive. So I have a quick cartoon here, right? So what you see here is like tree fork. That's the medial axis of the gray set, right? So that's the set of all points that don't have a unique nearest neighbor on the manifold. And then the reach is just the minimum distance of that medial axis to the manifold. Right, and you can probably even if you haven't seen this before, you can probably imagine that characterizes something about the geometric properties of that manifold. Right, so those are the kinds of measures that we take into account. This and regularity conditions on the manifold and the intrinsic dimension. Those are our sort of geometric characteristics that we're considering when we characterize the geometry of our input data. So now let me sort of preview here, or just give you an overview of the kinds of learnability results that we get, and then we can zoom in a little bit more on the different settings. So it turns out that in this sort of refined geometric setting for the data manifold, we do find instances where neural networks are actually learned. So if we put enough restrictions on those geometric characteristics that we just discussed, we can find manifolds on which feed-forward neural networks are efficiently trained. And that has something to do with how well that manifold can be approximated with samples. So we will make that precise in a second. What's important about this is that that goes beyond sort of the classical manifold hypothesis. So just assuming the manifold hypothesis by itself is not enough to guarantee learnability. In fact, we can construct hard instances, we can construct manifolds on which we can provably not learn a feed-forward neural network efficiently. So the manifold hypothesis is really not enough. We need this additional condition of efficient samplability that we will make precise in a second. And then what we also want to briefly discuss is now looking into, we are, of course, so from a mathematical perspective, those results are interesting, but we also want to understand where maybe real data might fall into this setting. And unfortunately, we think, and I will show you some sort of computational evidence towards that, that real data, unfortunately, will not quite fit in either of those regimes. So the geometric characteristics of our data manifold that we use here in the analysis probably have to be refined to really understand the kinds of heterogeneous data structures that we encounter in practice. So this is why we have this middle regime here, which we call potentially learnable, and where currently we don't have learnability results. So we can neither show learnability, but we can also not show hardness. So likely by refining this geometric analysis, we can maybe like reduce this middle regime and refine, sort of expand the hard and the learnable regime. Okay, so that's sort of in a nutshell the results. Now let's take a slightly closer look at what we mean by that. So as I said, the key ingredients to move to the learnable setting is this samplability condition. So basically what this means that for our input data manifold, we have to be able to construct an epsilon net with polynomial many data points. Right, so in a sense, we need to be able to sample a dense enough sample so that we have sort of good coverage of the manifold, construct an epsilon net, and then we are able to show learnability. That might seem like a quite abstract condition, but it's actually a condition that's that you can find in a lot of literature. So for instance, for manifold learning. So there's a whole literature in machine learning on how to construct manifolds from data. So again, working in this regime with the manifold hypothesis, and then thinking about if I have some data set, how could I start to reconstruct that low dimensional manifold on which the data presumably lies. And this problem of manifold learning has received a lot of attention. There's a lot of work in the literature, and all that whole body of literature makes a samplability assumption similar to this. Okay, so for instance, this paper that is cited here by Fruckerman, Miller, and Mariana, this is about testing, or this paper looks at when we can fit a manifold to data, what the sample complexity of this problem is. So there you need this assumption There's work on manifold learning algorithms, such as isomap, for instance, that also makes similar assumptions, and it shows that this is a necessary condition for being able to find a good reconstruction of the manifold. So this is not as abstract as one might think. Yes.
Can I just ask, what's the role of delta in the epsilon delta net? There's no way to use that epsilon delta net. You know what an epsilon net is? I think I know what an epsilon net is.
So this has to do with the. This has to do with the sample. Sorry, this is maybe not quite clear. This has to do with the sample size, with the sampling procedure. Yeah, you can just think of an epsilon. Yeah, so we're taking a sample from the manifold, right? So there's sort of some randomness in that. So there's some parameter related to that this has to be taken into account.
It's like an epsilon net with probability 1 minus.
Yes,
delta.
yeah.
Okay.
Sorry, this is not well stated.
Okay.
Yeah, sure question. Yeah. Okay, so and just to give the intuition here on like why this is important. So this is not quite how we prove this, but I think this is sort of building on that literature. Maybe gives sort of or as much of an idea as I can give in a short talk like this. So this literature on manifold learning gives us guarantees that under this simulability condition, we can in fact reconstruct the manifold. Now, if we want to learn a function over such a manifold, right, we could look at the graph of that function, and then we could apply the same sort of reconstruction and interpolation arguments that are used in that literature to the graph of that function, right? And then one can show that this samplability condition is in fact enough to also efficiently, in polynomial time, reconstruct or learn this graph of the function. Right, so a lot of the arguments that we're using here really build on like very classical tools from the manifold learning literature. I also want to give some intuition on the hard regime, right? So we said that the manifold hypothesis just by itself is not enough to guarantee learnability. And in particular, we can show that this samplability condition that we just discussed is really important. So just regularity conditions and a bounded curvature, bounded reach, and bounded intrinsic dimension is not sufficient, because we can construct pathological examples where we can show computational hardness. So similar to what we discussed in the first part of the talk, where we constructed certain classes of functions that sort of attain the exponential lower bound. Similarly, here we construct classes of manifolds that obtain an exponential lower bound. And the kind of manifold that we're constructing in the paper is, I have to be honest, very non-intuitive, like not something that you would encounter in practice. Just to sort of illustrate how it would look like in a very low dimensional setting, it kind of looks like something like this, right? So here we're in a ambient 3-dimensional space, and then the manifold is sort of touching exponentially many quadrants of the hypercube, and that exponential dependency that allows us to construct an exponential lower bound. So it's difficult to sort of without properly going through the details to really give an intuition on that. But what I just want to show is that this hard regime that we see here is really for pathological examples, and we were like not able to really construct an example that you would encounter in an application. So even though we have this hard regime under the manifold hypothesis, this other regime where we have the samplability condition is actually much more realistic, which I think is a good sign. So perhaps a lot of the sort of data manifolds or data sets that we encounter in practice are closer to the learnable setting than perhaps this hard setting. Again, some experimental results, right? So similar to what we saw in the first part of the talk. Again, here this is synthetic data, right? We construct, so on the right-hand side, the data set is similar to this manifold, this hard example that we just saw here. So something like this, just in a higher dimensional setting. And then on the left, so one example of a samplable manifold, for instance, would just be the hypersphere. So we look at the hypersphere and then train a feed-forward neural network, and then we sample from this pathological example and try to train a neural network. And then you see here in the learnable setting, this works really well, right? The network trains very nicely, so that sort of aligns with our theoretical intuition. And then in the hard regime, we see that in low dimensions, the neural network can actually compensate and does learn something. But then as we increase the dimension, the ambient dimension, we see that it can't train anymore. Okay. So certainly, again, those results, even though it's in a very controlled setting for synthetic data, does seem to align with what we see in theory. Okay, and the last thing I want to talk about is to think about the setting of real data, right? So we have these two regimes, the learnable regime and the hard regime. And we have from the theoretical analysis some characterization of the properties of a data manifold that would make a data set fall into each regime. But now what about the data sets that we find in practice? Unfortunately, measuring these geometric characteristics that go into determining on which regime you might fall, things like the intrinsic dimension, the reach, Ricci curvature, those kind of characteristics are really hard to estimate from data. There's, of course, been some work on this. Intrinsic dimension is quite well studied. And then curvature, for instance, my group has worked on estimating Ricci curvature from data. But what all of those methods have in common is that they have a quite high sample complexity. So typically, you need a really dense sample to get a somewhat good intuition on how these geometric characteristics might look like. And then, of course, if we look into a real data set and we have no idea on how the data manifold might look like, it's impossible to reach that sample complexity that would be needed to get a good result. So this is not sort of something that we can mathematically show, but sort of a computational way to get some intuition on this could be the following, is to use a diffusion model, right? And the diffusion model learns, in a sense, you could think of that as some sort of implicit representation of the manifold that we can then sample from, right? And we can, in principle, generate an arbitrarily dense sample with a trained diffusion model. So we can train a diffusion model on a data set, and then we sort of probe this representation that the diffusion model learns and try from that to learn something about the geometric characteristics of the data. So that, of course, includes a lot of assumptions in that the diffusion model actually learns a good representation and so forth. But if we put that aside, that's maybe one way of beginning to understand some of these characteristics and get to the kind of sample complexity that we need to actually perform this analysis. People have done that before us. So this paper here that I'm citing, Stensuk et al., that's from Caroline Schönlieb's group at Cambridge. So they have used this technique, diffusion models, to probe data manifolds. What we're doing here is, so we generate a sufficiently dense sample with the diffusion model, and then we use a standard approach for approximating the intrinsic dimension from data that's based just on PCA, so a very simple technique. And then here's what we find. So we look at 3 classical benchmark data sets: MNIST, that's handwritten digits; IK MNIST, that's Korean letters; and then Fashion MNIST is images of clothing. And we pick 10 classes from each data set, and then just do that local analysis to probe the characteristics of the manifold. And then what we find is that the intrinsic dimension seems to be quite heterogeneous. It seems to vary a lot across the data set. And that's not something that we see in controlled experiments. So if we train a diffusion model on a synthetic manifold where we can characterize the geometry precisely, then we see, for instance, if we choose something like the hypersphere, for instance, we don't see this heterogeneity. So this is just some hint or perhaps some evidence that the kind of geometric characteristics that would be needed to really characterize these data manifolds are much more complicated than what we have in our current hard and learnable regime. But I think it's sort of a nice way to start thinking about varying or heterogeneous intrinsic dimension, I guess, is something that we might expect here. But how we could perhaps start parameterizing geometric settings like this, and then perhaps think about where this might fall in our framework, if we can extend the learnable setting to these kind of settings, or whether any geometric characteristics might appear in real data that would put these input manifolds into the hard machine. So that's sort of a future work, just some computational exploration. Yes.
Question here. So what does it mean to have like a dimension of like 102? If you start from like that specific class of image, jump to like different images in the same class, or from one and then randomly generate some noise around it?
Yeah, so this is in the, so we look at one point, and then we look at the neighborhood of that point, right? We generate a dense sample around that point. And then, yeah, you don't want to just do that on one point, right? But sort of look at how consistent that is across the class. Yes. But yes, in order to do that, so sort of for locally, you need always a dense sample. So we pick one data point sort of as anchor, and then we use that diffusion model to sort of sample from what would be the neighborhood of that point on the data manifold. Sense.
So it also depends on how that like generated model is like producing those new points around that as well.
Of course, it depends on the diffusion model, and yeah, there are a lot of pieces to it. Yeah.
But to be fair, to disregard this as up or down, because the diffusion might then collapse things, you know. Like you did at some point, you have this dimension, but then they shrink back. So in other words, locally, it didn't go at that point. You follow a little further, the diffusion and then it's dimension collapse back. I'm saying it because there were several other estimates that in the older literature and for prior considerations, and this was like dimension between 10 and 20.
Yeah, so this was more classical. So like this work, for instance, and like so we're not the only ones who are doing this kind of stuff. So with the diffusion model based analysis, you typically get some higher dimensions, and then these older approaches are like they use more classical approaches, so they're not yeah. Oh yeah, just you mean that this overestimates?
Yeah.
Yes, sure. Yeah. I think that's right, that it overestimates. I'm not sure if it's quite as low as the other data sets say, but that this could potentially overestimate. I think so. Any other questions? Yeah. Okay, then just let me conclude with some discussion for the second part. So in the second part, we showed that the manifold hypothesis itself is not sufficient to ensure learnability. Right? We need some additional assumptions beyond just regularity assumptions on the data manifold, bounded curvature, and bounded intrinsic dimension. If we add in this samplability, efficient samplability assumption, then we are in the learnable regime. And then we discussed one instance that put us into this learnable regime, namely that setting that's considered in the manifold learning literature. So the sort of conditions that you need to reconstruct the manifold. And there are also other regimes actually. So our learnable regime is more general than the manifold learning regime. So for instance, there are settings where you have bounded Ritchie curvature, that also like practical settings where that is known to occur that I haven't discussed because we haven't defined Ritchie curvature. But so there are a couple of regimes that we can consider that fall into this learnable regime. And then, yes, we had some discussions. So with real data, we're not really sure where that might fall, but computational experiments on real data manifolds perhaps could give us some intuition eventually on what are these characteristics that we might need to take into account and how we could potentially expand the learnable and the hard regime. Yes, so that is future work. And then here are the two references for the first part and the second part, if you want to learn more. So this is joint work with many people. So Bobak is a postdoc in my group, and then Jason is an undergrad at the college, and then Teen and Hannah and Stephanie are at MIT. Thank you.